Okay, we are ready to talk more about probability and statistics and things. We've been talking about probability statistics and stochastic processes. And I'm really happy with the new microphone system here because I think that my voice comes across a lot nicer than it used to be. Let me share my screen. And let's go to the homework problems that we have. And where's my homework problems? There they are. Okay, so with this in mind, let's, okay, how come it isn't getting bigger? Can you guys see that? Is that okay, or should I make it bigger? It's okay, okay, it's okay with you. Okay, did anybody, I want to see what you've done here, generate a bunch of Y. I want to see your empirical results from the random number generator. Did you do this? Who chose something other than the exponential, or did everybody choose the exponential? Okay, let's have somebody show it. You did a cosine. Were you able to derive what the probability density function was for the cosine?
I think so.
Okay. Oh, that'll be interesting. Okay, let me get my coin flipper here. Unfortunately, I don't have my coins. I prepared except for my coins. Okay, so what I'll do is I have these pill pods here. When you get old, you have to take a bunch of pills. And so this will be heads and this will be tails. And Theo, you're 0, Glauco is 1, Adam's 2, Justin's 3, and Matthew is 4. It's hard to flip them randomly, but it's I don't know if this is fair. It's a 0, 0. Theo, I think these are biased, so they're always going to come up 0, 0, but let's go ahead and try. Show us what you got.
All right, I'll share my screen. I think
I have to give you permission. Yes, I do. I have to first of all stop sharing my screen, and then I need to give you permission to share the screen. Okay, good. So you should be good to go.
Great. You guys should see my homework now. So we start off.
How did you get white on black? That's kind of cool.
I do it on my iPad. Saves the battery. So we have a transfer function, g of x equals the cosine of x.
Okay.
And since we're doing our input distribution is a uniform distribution on 0 to 1.
Yes.
So we can say that the function g of x is monotonic over that domain. So we just have one term in this equation. So f sub y of y equals f sub x of x divided by the derivative of, I guess you would say, the transfer function, or the magnitude of the derivative of the transfer function. The uniform distribution is 1, and the derivative of cosine x is minus sine x. And then I did a triangle where x is an angle to figure out what, I did the unit triangle to figure out what would be returned in terms of y. So I got 1 over the square root of 1 minus y squared. So therefore,
okay, what interval is that? I guess it's from 0 to 1, right?
Yes, so that shifts the f sub y interval from, I think it's 1 to around 0.55, whatever the cosine of 1 is.
Oh, okay, interesting. Yes, okay.
Yes.
So at 1, there's literally a singularity. It goes to infinity, right?
Yes.
Which is cool.
Yeah, and I had to do a lot of points to get a nice curve fit. But anyways, so we have the f sub y of y is 1 over the square root of 1 minus y squared. And like we just talked about, we have to account for the domain shift. So the distribution in y goes from 1 down to roughly 0.55, which is the cosine of 1.
Yeah.
So here's our uniform distribution. So this is x on 0 to 1, and everything's normalized. And then here is f sub y of y, and you can see the red dotted line is this is a line that we just calculated, and then you can see if we transform each of the samples from x, they match up on the same curve.
Isn't that cool? Were you kind of surprised and kind of felt a completeness inside you when you did this?
I think it helped me to understand it. I was, it made more sense, like this transformed on random variables.
And that was the purpose of this. You know, you go through a bunch of mathematics, but when you go to the computer and actually perform the transformation on the random variable, it becomes much more real, doesn't it?
Mm-hmm.
Yeah, so that's nice. Excellent, excellent, good stuff. Okay, I have changed my my coins to I don't know, these stick 'em notes. So let's see what happens here. Heads, heads. That's 1-1. Who's number 3? 0, 1, 2, 3. Justin, I think that's you. Can you show what you did on this problem?
On this one?
Yeah.
Okay, yeah, so I just did the exponential. I tried to do the Cauchy. So I was like, if you have a uniform distribution, you're trying to transform it to that, you can set g of x to be the inverse of the CDF.
Right.
So I found the CDF, which is this 1 minus e to the minus y. And then I take the inverse of it, and I got that. And then by applying that to the uniform distribution, I got an exponential. That worked out nicely. I tried doing the Cauchy, but it was kind of being rude with me. It wasn't working out.
Okay.
But I don't know. I feel like I did this, and then I was thinking that it was wrong, so I tried to look it up online, and I found something online, and it agreed with me on that this is the correct g of x. So I don't know. Maybe I was just trying to plot it wrong.
Yeah, I have no idea what you did. Yeah, why it didn't work out for you. So, but anyway, you did get the exponential to work correctly.
Yeah, I got the exponential to work.
Okay. Did anybody do the exponential and plot the results versus the e to the minus x? Did anybody do that? Like Theo did his, and he compared the histogram, the normalized histogram, to the actual PDF. Okay, Glauco did. Okay, Glauco, you go ahead and take it, and let's see how you did. Very good, Justin. Perfect.
I think this is the same thing as.
Okay, make your screen just a little bit smaller so we can see it.
Yeah, I'm trying.
Okay.
So I got e to the x as the transformation, and this is the f sub y is 1 over y, and I plot it in orange here. And then I use a lot of points, like 10 million, so it's very exact. It goes through the middle.
Okay. Well, this is very interesting. Now, you see that this histogram conforms to the theoretical result, right? This is something that we're going to revisit very soon, maybe in the next week or so. It's called the law of large numbers. And it's very interesting that in probability that there are deterministic results. There are deterministic results. One is that your histogram will converge with probability 1 to your theoretical result. Now, the interesting thing is that there is a possibility that you could, it's a very low probability, that you could generate 1 million random numbers and they would all be, say, on a uniform. 1 million random numbers and they would all be between 0 and 0.1, right? As opposed to between 0 and, but there's a finite probability that that would happen. And in that case, that transformation that Glauco is showing here wouldn't work. All of the histogram would be clumped up on one place. But we are assured by the law of large numbers that this doesn't occur. So we don't say that the histogram approaches the probability density function, but the histogram approaches the probability density function with probability 1. So there's different types of convergence, and the convergence of the law of large numbers is a specific type of convergence, and there is a chance that it won't work, but it will work with a probability of 1. Very interesting result. How come you stopped at 2.75, Glauco? You could have gone further, couldn't you?
No, because the transformation, I was using the uniform between 0 and 1. So you don't have numbers to go further, because when you get to your bigger data X,
Oh,
you
e to the x.
transform it
Okay, I see.
to
I
X.
see. Okay, you're just doing, so what you're doing is the transformation that gets you to 1 over y.
Yes.
Very good. Okay, very interesting. So 1 over y would go from
1 to 2.75.
right.
A little bit less.
Okay. Okay. So anyway, it's kind of good that your two things match. Anybody do anything else other than the exponential? Okay. Well, that's good. Very interesting. And I hope it was instructive, and I hope it clicked something in your head to connect all of this mathematics to what we're doing here. Collected I'm sorry, I was talking while I was clicking, and I'm not getting very good at sharing, multiprocessing here. So, okay, so that is this homework. The next homework is, what is the distribution of these random variables when the following case? What's if you take 6 geometric random variables with a given parameter p, what does it converge to? Can anybody just answer with a name, with a word?
Pascal.
Pascal.
It goes to a Pascal, doesn't it? Isn't that interesting?
Mhm.
What about 6 Bernoulli random variables? Well, with parameter p, what does it converge to?
Binomial.
Binomial.
Binomial. And in fact, that's the definition of binomial, right? The number of successes that you get well, in this case, in 6 Bernoulli trials, you get a binomial random variable. And what's interesting in that is that the characteristic function verifies that indeed this is the case. 6 negative Pascal negative binomial random variables. What do you get?
I got still Pascal negative binomial, but with the sum of all the different R's as the number.
Yes, that's exactly right. You get a Pascal random variable with a parameter p, but the R's are all different. And what you get is the sum of the R's, don't you? The new R is equal to the sum of the old R's. And this is the interesting thing. 3 Gaussians, all with different means and variances. You get a Gaussian. What is the new mean?
Sum of the means.
Sum of the means. And what's the new variance?
Sum of the variance.
Some of the variances. That's right. So the interesting thing is that anytime you add a Gaussian random variable, you get a Gaussian random variable. And we've also shown that's the same thing for the Pascal negative binomials and a number of other random variables. Turns out it's true for the Cauchy. I should have assigned the Cauchy. Do you remember what the Cauchy the Cauchy characteristic function is? It's a Laplace. It's e to the minus, and it turns out if you add Cauchy random variables, you get another Cauchy random variable. So that's very interesting. Does that make sense to you? Okay, I think that's pretty fairly straightforward. The characteristic function for a Cauchy random variable is of this form. Right? And if you add up capital N of those random variables, let me do it this way. you add up a bunch of those random variables, and we'll call this summation y as a function of omega. Well, each time we add one, we multiply the characteristic function. So this is n alpha o times omega. In other words, it's equal to phi sub x raised to the nth power. So what is this? If this is a Cauchy with a parameter of alpha, then this is a Cauchy with a parameter of n alpha. Right? So Cauchys are also conserved here. This is, I find this fascinating. So even if Cauchys are weird, they add up together. What happens if you add Cauchys with different parameters of alpha?
They add.
They add, right. Your new alpha is equal to just the summation of these alphas. And I have no idea why I'm writing on a 45-degree line here, but you get the idea. So we do have this interesting result. Adding Cauchys gives you a Cauchy. Okay, with that then, let's go back to the homework and let's see if we can get the last one. The last one is the most challenging, I think, of the ones that we talked about. Or not the ones we talked about, but the ones that were assigned as homework. And the last one is, what is the mean invariance when the characteristic function is this exponential? And n is an integer. What can I say about that? I'll say something interesting. I'll say that if n here, if n in this expression is equal to 1, then we have a Cauchy random variable, right? If n is equal to 2, we have a Gaussian random variable. If n is equal to 3, I don't know what it is. But we know that for n is equal to 1, it's really weird because we have a Cauchy random variable, which has all of its strange properties. For capital N equal to 2, we get a Gaussian, which is a very well-behaved function. So does anybody want to tackle this one? If not, I'll go ahead and drop my pseudo coins here. This is cryptocurrency. Uh-oh, it does not look like it is random because I'm getting 2 heads again. 2 tails. Well, we've had 0, 0 already, so. Heads, heads. We're going to try it one more time, and if this doesn't work, somebody that hasn't talked should talk. Heads, heads. Okay, somebody who hasn't talked, go ahead and talk. Anybody get this?
Yeah, I got a solution, I guess.
Okay, I'm sorry, who's talking? I didn't see the
It's
talker.
Adam.
Adam. Okay, Adam, go for it.
See, can you unshare?
I can unshare.
And I want this window. All right. So, zoom in a bit here. So I use the property of the second characteristic equation, where you take the derivative, it's equal to j times the expected value, and the second derivative at 0 is the negative variance.
Okay.
So the first derivative of the second characteristic function is the derivative of the natural log of the characteristic function, which is the derivative of the characteristic function over the characteristic function, both evaluated at 0. So take the derivative of the characteristic function it gave you. It's this lovely equation here. Plug in 0 for that, you get minus j. You plug in 0 to the original equation, you get 1. So j e of x is minus j over 1. So e of x is minus 1.
Okay, there's one problem here, and that is in your derivative of the characteristic function. Your derivative of the characteristic function, let's see, is that right? Yeah, your derivative of the characteristic function, if you were to plot it out, literally has a discontinuity at the origin, right?
I guess he has an absolute value there, yeah?
Yeah, if you have it for, say, n is equal to 1. And so you have a discontinuity. So the characteristic function is a double-sided exponential. If you differentiate it, you're going to get whoop and whoop. You're going to get an exponential on one side and another exponential on the other side, which is flipped around. And therefore,
They'd
you
both
have
be approaching 0. wouldn't they?
well, no. You have to ask yourself, what is the value of a discontinuity at the origin?
Hmm.
Okay.
Yeah.
What is the value of the discontinuity at the origin? And it turns out that in all the cases where capital N is odd, you're going to get that discontinuity.
Hmm.
For all cases where N is odd, you get that discontinuity at the origin when you differentiate. For all even cases, it's a piece of pie or it's a piece of cake. I had a Korean student one time and I said, this is easy. This is a piece of cake. He said, this is not a piece of cake. And he was right. This is a piece of cake. Glauco, have you heard that Americanism? That,
I don't know, but it makes sense.
okay, a piece of cake is something which is very easy. It's a piece of cake. Yeah, so odd, you get a different result. For all of the odds, the mean is undefined because all of the odds are going to have a discontinuity at the origin. All of the evens are going to be continuous at the origin. All of the evens are going to be continuous at the origin. So, man, I'm getting so many robocallers. So that's the case, right? Odd, you always get the discontinuity at the origin. For the even, everything is fine. The odd is like the Cauchy for n is equal to 1, where you get an undefined mean and an infinite variance, because if you differentiate that discontinuity a second time, you get a Dirac delta there, right? You get at the origin, you get the Dirac delta, and that only occurs for odd. For even, you don't get that. So did anybody do that to the extent that I just mentioned? Okay, do you understand my explanation to the point where you think you can redo it? Or would you like further elaboration? I can elaborate further if you'd like.
I would appreciate some further elaboration.
Okay, elaboration. Never hesitate to elaborate, right?
Thank you.
Okay. Yeah, here is the situation. We have e to the minus omega raised to the nth power. Now there's this e to the j out here. I'm not going to worry about e to the j. You can put that in. I'm just going to do it without any e to the j. Is that okay? Now, the question is, if this is the characteristic function for omega, what does this look like? Well, for n is equal to 1, it kind of looks like this, right? This is the result as a function of omega. By the way, the characteristic function at the origin is always what? 1, right? That's the value of the characteristic function at the origin. But this is also going to be 2 for 3, 5, 7, 9. In other words, any time that you have an odd exponent here, omega to the n, you're going to get kind of a cusp here at the origin. It's not going to be continuous. It's going to be a discontinuous first derivative. We know for a Gaussian, the Fourier transform of a Gaussian, the characteristic function of a Gaussian is a Gaussian. It's nice and smooth. There is no cusp. So this is going to be true for n is equal to 2, 4, 6, etc. Does that make sense? And over here, you have to make advantage of the idea that omega, here's the way to think about it, is equal to the omega times the sign. Everybody know what the sign is? The sign is 1 for positive values, minus 1 for negative values. And if omega is odd, you have omega times the sign of omega, well, raised to the odd power. And you have the sign raised to the odd power also. And if you raise sign to the odd power, you think about it, you either get a plus or a minus sign. Anybody know why we call this sign, by the way? We call it sign because it should be the sign, S-I-G-N, but it turns out the sign is already taken in terms of the trigonometric function, so we don't need to worry about this. So you're going to get like one raised to the odd power, right? You're going to get the sign. You're going to get 1 raised to the odd power. Oh, I guess 1 to the odd power is always 1, and you're going to get minus 1 raised to the odd power. And I guess that's always equal to minus 1, so I guess it's always just sign. Right? So therefore, that's good there. But if you get over here where omega is equal to even, and you get omega to the even times the sign of omega to the even. Well, anytime you have plus and minus 1 raised to the even power, you're going to get 1, right? So this is always going to be equal to 1. That's always going to be equal to 1 because sign raised to any even power is always going to be equal to 1. So that's the reason we don't even have to worry about this sign here. We do when it's odd, we don't when it's even. So just graphically what happens is that anytime you differentiate this, you are going to get a curve which looks like this. This is the, well, I don't know, should we do the first or second? We'll just do the first characteristic function. We will go through the phi sub x prime. So if you have an odd power, you're always going to get this discontinuity. And you need to evaluate this at the origin, but we can never evaluate this at the origin because at the origin, there's a discontinuity. Yeah, you could take the arithmetic mean point, but that's not the same thing as evaluating at the origin. The mathematician would say, no, that's totally undefined. Whereas over here, if it's even, here's the odd column, here's the even column. For the even, you're always going to get something which is very nice. It looks like the slope here is going to be negative, so the derivative is going to look like this. And it does turn out that that this is very nice and continuous if we do the phi x of omega for n is equal to even. The problem with it odd, if you go to the second derivative, which gives us the second moment, we are going to have a e to the x, which is an e to the x. We're going to have a minus e to the x, which is e to the x. But the derivative of this discontinuity is going to give us a big fat delta function here at the origin, right? It's going to give us a big fat delta function at the origin, which is always infinite. So therefore, the second moment is always infinite when omega is odd, just graphically, if you will. Whereas over here, if it's even and everything is nice and smooth, we see that we get a nice positive slope. I don't know exactly what it would look like, but it'll probably look something like this. This should be prime. So we're going to get something which is nice and smooth, and we're going to get a value at the origin which is going to be a finite second moment. Okay? So hopefully that explains the general methodology of working this. It makes a difference whether n is even or n is odd. Any questions on that at all?
I guess we would solve that in like kind of like two cases. One assuming n is even, one assuming n is odd.
Yes, that's the way that the math turns out.
Mm-hmm.
Because if n is odd, you get a discontinuity. If n is even, that not discontinuity, you get this cusp here. You get a discontinuity. You get a discontinuity in the first derivative. Always, you get a discontinuity in the first derivative. But if n is even, then that SIGN goes away, and we just start performing an operation on something which is nice and well behaved. So that's the reason over here for n is equal to 1. As we said, we get the Cauchy. We all know the problems with the Cauchy. We've seen this sort of graphs with the Cauchy before. For n is equal to 2, it's equal to the Gaussian, which is one of the most beautiful probability density functions. By the way, people in statistics call this the normal. So if you've ever seen the normal probability density function or a normal random variable, it's the same as what we're calling a Gaussian random variable. And for n is equal to 2, the Gaussian random variable is very nice and well behaved, and we don't have to worry about it. And that's the same thing which is true for n is equal to 4 and n is equal to 6. Same thing over here for the odd. N is equal to 1 is the Cauchy, that's bad. N is equal to 3 also gives you this discontinuity. And for any odd value, it gives us a discontinuity. It's a curious result. It's one which is not intuitive at all to me, but this is what the math says, and we believe the math. Any other questions? Okay, if there's no other questions, let's go ahead and finish the homework and get it in by, say, tomorrow, okay? Because we have to allow Adam time to take a nap. He was up all last night, right? You still doing good, Adam?
I'm still here.
Yeah, the Alamo is well lit behind you, but we can't see your eyes, but I'm sure that they're doing fine.
There you go.
Okay, good. Okay, let's continue with our lecture from last time. And let's continue from where we left off last time. I believe this was the last slide that we talked about. This is computing, if you will, the minimum of two random variables. The beautiful thing about the joint probability density function is you can compute any relationship between the two random variables. Like before we did the probability that one random variable is greater than the other. We could get that by integrating the joint probability density function. Before that, we got the probability that x is less than or equal to x, and was able to derive the marginal from that. So anything you want, any relationship between x and y, you can obtain through the joint probability density function by choosing the appropriate place, appropriate area of integration. And this will take you back to calculus, where you did two-dimensional integrations, if you remember. Let's talk about point masses. Point masses are characteristic of discrete random variables. And again, I like to use discrete Dirac deltas because they're so beautiful, and it unifies all the probability density all the probability arguments into just the probability density function and the characteristic function. We don't have to worry about Laplace transforms and Z transforms and other things. So this is what the two-dimensional Dirac delta looks like in 2 dimensions. It's a point mass. Now this is a del of x minus x naught. You see that there? Now let's look at del of x minus x naught. We can think of this is one way to do this, is we can think of it as equal to infinity for x is equal to x naught, right? And we think it as 0 everywhere else. This is a loose definition, but gets us to where we want to go. Well, what is del sub x minus x naught equal to infinity? Where does that correspond to? Well, all along this line here, independent of y, x is equal to x naught. All along this line, right? So all along this line gives us a Dirac delta, and you can think of it as a knife edge. It's a knife edge kind of pointing out at you. And that's what a one-dimensional probability, that's what a one-dimensional Dirac delta looks like in 2 dimensions. On the other hand, the del of y minus y naught is a big knife edge that comes across and cuts horizontally. And when we multiply these two together, the only place that one or the other is not 0 is at the origin, right? So when we multiply this up and down knife edge by this right and left knife edge, one of the variables is equal to 0. So everything goes to 0 except for this knife edge, or except for the intersection of the knives, which is right here. So we interpreted a del of x minus x naught as kind of a needle, if you will, sticking out of the xy plane. And this needle is the intersection of these two knife edges. So we just think of 2-dimensional Dirac deltas as point masses, if you will, on the xy plane. What is the volume of this? So if we go back, what is the volume of this thing on the left? What's its volume? Well, the volume is equal to its integral. So we have the integral of this. And because these are independent, we can break up the integrals into the integral over x and the integral over y. And we know in both cases, the integral over a one-dimensional Dirac delta is 1. So this first integral is equal to 1. This second integral is equal to 1. Is that okay? So the volume is indeed equal to 1. The volume of a Dirac delta is equal to 1. Just like in one dimension, the area of a Dirac delta is equal to 1. So instead of one-dimensional Dirac deltas, now we have a surface and we have little pins protruding from the plane, and these are point masses and correspond to 2-dimensional probability masses, if you will. Let me go, because this is very distracting with all the underlines here. Let me go to the slideshow presentation. If we talk about probability mass functions, now the probability mass function is equal to the area under a value. Say we have an x sub j here and a y sub j here. And we have, this is the x-axis, this is the y-axis, and we have a Dirac delta coming out here. This Dirac delta we know has a volume equal to 1. However, we can change the volume by multiplying it by p of xi yj. And this then becomes the volume of this. So this is p sub xy. If we're doing it on a probability density function, it would be this. I think this should be a k and not a y. Right? It is a Dirac delta needle at xi and yk, but it has a volume of the probability of whatever this probability is. And we can think of then a probability mass function, if everything is discrete, as being a bunch of Dirac deltas coming up out of the board here. Each one at a different point. And some are going to be a lot bigger than other ones, right? So we have a number of Dirac deltas coming out of the board. And if we were to add up all of these probability masses, you remember that the total area of a probability density function is equal to 1. So if we add up all of these probability masses under all of these Dirac deltas, they would sum to 1. And if the events are independent, then we know that this happens, because if they're independent, this is equal to the probability that x is equal to x sub j times the probability that y is equal to y sub k. This is under the assumption that the two random variables are independent of each other, okay? And if they're independent of each other, these individual random variables look like this. So the probability masses are the product of their one-dimensional equivalents, or their one-dimensional components, I should say. Now, the way that I've drawn it here, xj and y sub k can be any number. I'm getting an Amber Alert. Are you guys getting Amber Alerts?
Yeah, I just got one.
Okay. I don't think I can help, but maybe I can. Okay, random variables of the lattice type. This is something that I teach, but just not taught in Garcia, is random variables of the lattice type is where all of these Dirac deltas exist on integer pairs. So we have 1, we have 2, we have 3, whoops, 3. This is the x-axis, we have the y-axis, 1, 2. If they're of the lattice type, all of the probability masses exist on the intersection of this grid. Is that okay? And we've seen that in the one-dimensional case, there's many cases like the Poisson, the binomial, and other random variables wherein all of the locations of the Dirac deltas exist at integer values. But this is a specific case of this more general type. Generally, we can have the Dirac deltas anywhere we want to. The only constraint is that the masses all have to add up to 1. Okay, here is the two-dimensional discrete PDF. This is something we've alluded to before, where each of the probability masses is assigned to a Dirac delta at that location on the plane. So we have a number of Dirac deltas, and all the areas under all these Dirac deltas have to add up to be equal to 1. So this is just an explicit representation of what we've looked at before. And this is the example of the lattice type. For the lattice type, notice that we can only have values at integers. That is, x has to be equal to j and y has to be equal to k. They can't be arbitrary. So that's the lattice type. Now there's really weird sort of random variables. We're going to look at one here. Let's say that we chose a let's suppose that we chose a random variable x, and that random variable x could be anything. Maybe it's a Gaussian, okay? So this is a random variable x equal to this. Now we're going to assume that x is the length of a side of a cube, and we're going to define a second random variable equal to y, which is the cube volume, which of course is that random variable raised to the third power. Now, are these two random variables independent of each other? Absolutely not. In fact, they're so dependent on each other that if you give me the first one, I can give you the second random variable. They are dependent on each other. And what does this correspond to? Well, it corresponds to, this is kind of weird, but if we think of a knife edge over the value, this is the locus, y is equal to x cubed. The locus, y is equal to x cubed. And along here, we have a Dirac delta knife edge. So you can think of it as a Dirac delta knife edge that's kind of bent, if you will, along y is equal to x cubed. And then what we do is we modulate the height of that Dirac delta knife edge by the Gaussian here. And that turns out to be, yes, the two-dimensional probability density function where we actually have a line mass instead of point masses. And that's where we have 100% dependence. Theo.
So if that's the case, would this this probability density function that we see, that's just a projection onto the x-axis, and we're seeing it from the side. Is there ever a way to somehow put it in dimension, like to plot your PDF along as like a projection along the locus y equals x?
Along the x and x axis? Yes, indeed. If you take this random variable, let's see. I guess I can't do this. Remember, if you project along this interval, that is, if you project along this integral, you are going to get on this axis. Oh boy. I don't know how I can do this. No, I don't want to do anything. Okay. I'll try here. We'll see this. On this axis, remember the marginals. If we were to project parallel to the y-axis at all points, we would get, remember the marginals? We would get exactly this f sub x, right? If
Yes.
we were to project along this axis, we would get f sub y. Or f sub y of y, I guess it would be. If you project on this axis, you get f sub y of y. And what's interesting about that, you remember our transformation on the random variable, if we let y is equal to x cubed, and we went through that random variable transformation, and we got an f sub y, that f sub y through the random variable transformation would be exactly the same as the f sub y we got here. So f sub y and f sub x are the marginals of doing this, which is kind of interesting, right?
Thank you. Thank you.
Okay, good. So here's a question. Is this thing a probability density function? Looks like I've written over stuff. No, I guess I haven't. Okay. Is this a probability density function? Well, let's integrate first over the x-axis, okay, or the y-axis, right? To make sure it's a probability density function, what must the volume of this knife edge be equal to?
Be 1.
Should be equal to 1, right? So I'm going to make the integration over x and then y. Is that okay? Whoops, I'm sorry. This should be dy dx. I got my differentials backwards. I hate when I get my differentials backwards. Well, what is this equal to? Can anybody tell me what this is equal to? Don't forget, you treat x cubed as a constant here. So this is the area under a function where y is equal to x cubed, and there you have a Dirac delta. What's the volume here, or the area? I'm sorry, not x sub 3, x cubed. I'm moving too fast here. Okay, that doesn't work. So this is just a g of x, if you will, or g of y. So g of y has, for a given value of x, has a Dirac delta at x cubed. What's the area of this always going to be?
1.
1. It doesn't matter where that Dirac delta is centered. It's going to have an area of 1 if we integrate from minus infinity to infinity. It's going to have an area of 1. So all this integrand here is equal to 1. And so we are left with the integral of f sub x of x dx, which is the area under a PDF, which we know is equal to 1. So yes, this does have a volume of 1. It looks kind of weird, but it does have a volume of 1. So with that, any questions on that at all? Okie dokie. Let's go to conditional cumulative distribution functions in PDFs. That is, you are given a x and y, but somebody comes along and says, you know, before the random variables could appear all over the plane. But I'm telling you that the random variables have to occur within this region. So you're given that the random variables exist in a specific region instead of all over the plane. That gives you more information. So that should allow you to do something interesting. So let's talk about a conditional cumulative distribution function. This looks kind of scary, but it's not that big of a deal. Let's take a look at it. This is a conditional cumulative distribution function given that x and y lies within an area of A. In other words, you're given an x of y, x and y, but somebody comes along and says, hey, guess what? I can tell you that this random variable lies in this region A here, so you don't have to worry about it appearing everywhere at all. We know that it appears in this area A, correct? Well, this is, if you remember, the cumulative distribution function is related to a probability. In fact, it's defined by a probability. So this is the probability that x is less than x, and remember that comma is always an and y is less than y, given that x, y is within this region that people have specified, this region A. Now here we have nothing more than a conditional probability, and we can use the definition of conditional probability to write it this way. So this is all well and good, and we can apply it, but I think what I'm going to show you is going to be more memorable than this. And that is the conditional PDF. The conditional PDF is equal to the derivative of the cumulative distribution, just like before. And I'm going to give you a nice geometric interpretation of this, which will make it, I think, a lot easier than just looking at the math. To do that, let's go back to our histogram. Remember our histogram of trucks, the tonnage versus the length? We took this whole thing and we can make a probability density function out of it by normalizing it, if you will, a cumulative, not a cumulative, but an empirical probability density function. But somebody comes along and says, you know, I'm not interested in all the lengths and the tons. I'm only interested in the occurrence of this at a specific place. I'm only interested in trucks weighing between 1.5 and 2 tons, and a length between 9 and 10 feet. So that's all that I'm interested in. So all of a sudden what that does is that focuses you in onto a sub area. And this sub area is what? This is your A, if you will. You're given that the random variable exists within this sub area. And so what do? You make a conditional PDF. And what you do is to make the new PDF, the conditional PDF, what do? You take this thing and you assume that that's your whole universe. So you don't worry anything about the histogram out here, right? You don't worry about the histogram out here because you're just focused in on this area of A. And just like before, you would take each of these numbers and divide by the sum of the numbers in order to get an empirical distribution over the interval A. It's just like you're starting over with a different empirical histogram. Does that make sense? So that's the idea of conditional with the idea of these trucks versus the length and the tonnage. So here's the way to think of it in a continuous sense. We have an f sub x of y. This is a two-dimensional probability density function. It covers the entire plane, okay? It's here might be the contour plots of it. It covers the entire plane. But we are not worried about it over the entire plane. We want the conditional probability density function that the random variable lies within inside the area A. In other words, this area A. To do that, we keep the shape of the probability density function, the joint probability density function, and look at it only over A. So you can see the total probability density function probably keeps on going down here, and it probably keeps on going up here, and it probably keeps on kind of a constant here. But that's outside. We're only interested inside A, but we keep exactly the same shape. That's exactly what we did for this, right? We kept exactly the same shape within the small area. The structure is exactly the same. So we're keeping these values, but there's a problem with it. Once we keep these values and keep the shape of the cumulative probability density function over that area, we no longer have an area of 1, do we? In order to make that a bona fide probability density function, we have to do something to that little slice over A to give it an area of 1. And that's exactly what we do. The conditional has the same shape within the given region of A as the joint probability density function at 0 otherwise, and it's normalized. We have to multiply this thing by a constant so that its overall volume is 1. That's a requirement for it to be a probability density function. And a conditional probability density function is the same has the same properties as a probability density function. It has to have a volume of 1. It has to be non-negative. So in order to do that, what do? Well, the new density function, the conditional density function, if it exists in A, is exactly the same shape as the original density function, but we have to multiply it by a constant. Why do we have to multiply it by a constant? To get that total volume up to 1. We have to multiply it by a constant to get that volume up to 1. And we can do that volume simply by integrating over the area. We can get this constant by integrating over the area of the density function, and then that's the result. Where's my, oh, I guess I don't have a next thing. So it turns out that the total density function, where's my cursor? There it is. So the total density function, f sub x sub y, shoot. Let me start again. Okay, I'm not going to start again. remember, this is the total density function X and Y, and we're given that the random variable exists in some subregion A. This is exactly equal to the density function This is exactly equal to the density function of X and Y, but we have to make sure that X and Y is within A, right? And then we have to scale it some fashion. We have to scale it in some fashion that this has a total volume of 1. And we scale it by integrating by the area of A. Let me do this different. This is f sub xy. This makes it a little bit more clear, hopefully. Let me tell you why this makes sense. If we go back here, what is the volume of this thing? What is the volume here? That's the volume of A, right? So if we take f sub x of y, this is really, really good because it has the same shape, except we divide it by the volume under A. In other words, we divide by whatever this volume is. It's divided by whatever this volume is. And then what happens? If you integrate over this new density function, what does the top give you? If you integrate over this new density function, what does the top give you? It gives you the volume under A, right? And so you divide by the volume under A, so it gives you a total volume of 1. It's that simple. Any questions at all? That's conditional density. And that's a lot of fun. What am I doing here? I don't want slideshow help. I think I hit the wrong button. Okay, this takes us on to the next topic, which are cumulative distribution in PDFs. We've talked about marginal independence, functions of several random variables. I don't think we're going to go into that, and multidimensional expectations. We're dinking here with the idea of going on to an unbounded number of random variables. In other words, just not 2 random variables, but many random variables. That's what the purpose here is, multi-random variables. So if we had 20 random variables, and we'll deal with multidimensional expectations and multivariate Gaussian random variables, which is probably the most important part. Just a little tease that if we go to the cumulative distribution function of, say, n random variables instead of 2 random variables, we get something which is crazy. We get something which is what we see here. Now you notice that that x here is actually a vector. And that vector contains all of the independent random variables that we need. So X contains all of the random variables that we need. Capital X is the vector of the random variables, and X is a vector of the dimensions in which we are playing around with. You notice on the right there, that's the probability that the random variable is less than X. And how do you say that one vector is less than another vector, right? Vectors do not have inequalities. But by this, we mean what you see here on the second line is that the probability that x1 is less than x1 is less than x. I tell you, when you're describing math, never read out the equations, okay? Because it gets very boring. Here's the problem that we have. We have this vector, and this vector is given by X. The probability that X is less than X here means that the probability the first variable is less, the second one is less, the third one is less, and all of these commas are read as and, logical ands. So it's a probability that this is true, and this is true, and this is true, and et cetera, et cetera. And the X, as you can see here, is a vector of length n. And so this is one, two, many, isn't it, right? We've gone through one dimensional, we've gone to two dimensionals, we're going through many, many dimensions now. And just like in one dimension, we can get the probability density function in a high dimensional space by differentiating the cumulative distribution function over all of the variables. I don't know if you remember that if we had an f sub xy as a function of x and y, that if we set y is equal to infinity, or let's say x is equal to infinity, I think that's probably better. If we set x is equal to infinity, we went to just f sub y. You might recall that. And I think that probably we'll go ahead and stop here, because we'll talk about next time that you can get a lower dimensional probability density function from the higher dimensional probability, not probability density function, cumulative distribution function, by evaluating some of the arguments at infinity. And this is a straightforward generalization of the two-dimensional case. Anybody have any questions at all? Okie doke, I'll be assigning some additional homework, which we'll work on next time. Get your homework into Box by tomorrow. And we'll go ahead and continue the next time we meet, I guess next Tuesday. So if there's no questions, bye-bye, be of good cheer. Okay, yeah, okay, bye-bye. I was going to say don't swallow any armchairs, but